add, and almost done. I'll just do an overview afterwards. So you got silver chloride solid plus what's left is ammonium acetate, which you're going to have to squeeze up, and that's going to be aqueous. Right, and I might just move that over. Right, and this all looks 1-to-1 ratios. I don't know why I put that minus sign. It's been cancelled out by the positive. I didn't check for balancing the previous one. I seem to do that on every fourth one. So we got, what we're going to do is put a 2 there and a 2 there. And I didn't have a 2 there. So plenty of mistakes in question 27. Apologize for that. And there might be the odd mistake here or there, but more or less these should be the answers. And what an overview. What have we actually learned? So looked at quite a lot of reactions. We did the odd synthesis reaction and decomposition reaction. They're pretty much just identification. You're not going to learn too much from that. We did a few precipitation reactions towards the end. That's when you mix two salts and you produce one solid. That becomes a lot easier when you start learning about solubility and you start looking at, ions bumping into each other and making ionic compounds and water splitting them apart and all that kind of stuff and what's actually happening there. We looked at, towards the end, we looked at a few neutralization reactions. So I did a tiny bit up here on acids and bases. So you got an acid is anything that, this is actually a bit of year 12 stuff. So if you don't understand that too much, don't stress. But anything that when put in water, if it makes this compound, which is called a hydronium ion, which is a word you do not need to know for a long time, this just basically bumps up the hydrogen. So water is obviously 2-to-1 ratio with oxygen, and the extra hydrogens make that water reactive. And so you want to keep track of that when you're doing, if you're putting your hand in it, if your fish are living in it, like scientists and people need to know how much extra hydrogen is in that solution. And actually, if there's a heap of that, you have a really low pH, because pH is the negative log of the concentration of the H2O plus. And similarly, if you put in all these OH minuses, by default, they bring down the ratio because they're just a 1-to-1 ratio. And that can also be dangerous because this OH, if there's a lot of them, they actually go up to your cell membranes and pluck off hydrogens from your cell membranes. And if they pluck off a hydrogen and change the structure of your cell membranes, then that structure of that cell is compromised and all its contents spill out like a balloon popping. And that's kind of what you've seen in movies when hands dissolve in strong acids or strong bases. What's happening is they're reacting with the compounds in your body and causing them to change shape. And if their structure is compromised, then their three-dimensional robustness, their shape, their hardiness gets destroyed, and they become soft, gooey jelly. So you need to worry about both ends of the scale. And yeah, so this is year 12. And so I put this actual reaction in neutralization. It's just literally the extra hydrogen reacting with the less one and coming back to water. And it's called neutral because it gets you towards pH 7, right, which is neutral green in the universal indicator. Then you got acid plus metal. Acid plus metal is every time if it reacts, it produces solid and hydrogen gas. And then in year 10, we get you to do the POP test to confirm that invisible gas is hydrogen. So the POP test is literally reacting it with oxygen. It's actually what rocket fuel is. H2 plus O2 going to two waters like this. Gas, gas, gas. This is the POP test. You may notice that when you do the POP test, it obviously releases that audio, the pop, but you might also notice that it leaves a droplet or two of water. And the reason why I'm bringing that up is because a large volume of gas can produce just a little bit of liquid, right? Because there's about 1,000 factor difference in the volume that it occupies. And that's the POP test. And then we did a bit on acid plus metal carbonate, where you get three products: carbon dioxide, salt, and water. And in this one, you can test for that carbon dioxide by doing what's called a lime water test, where you literally get that CO2 and you bubble it through lime water, which is actually calcium hydroxide, lime water. It's kind of aqueous, kind of semi-soluble, and it produces a white precipitate calcium carbonate. In other words, to say you see little white solids, and no other gas does that. So because carbon dioxide does this, what do I got left? Calcium carbonate plus water, right? And actually, I think it's hydroxide. No, that can't be right. Why am I not remembering? It's either, I think it's OH. Probably figure it out quickly, but not on the spot. Yeah, I'm just going to go water. I think it might be OH. Anyway, this is a confirmation for the invisible gas. And then we go into complete combustion and incomplete combustion, which has to do with the amount of oxygen present. And you might see in my example, I've done an example where you get carbon monoxide and soot in the same one. Right. Okay, and that does it. There's a lot going on there, but in summary, what you kind of get out of this is that there's all these types of reactions and they can help you predict the products. There's all these like polyatomic ions and acids and bases that you've got to start getting into your memory. And there's also solubility that you're starting to work towards. And you can start to write out pretty little equations like that. And these become really useful because they tell you the ratio that particles react. And then once you get on top of that, you can start getting to figure out how many particles you're working with when you say have 10 grams of it. So chemists want to know the ratio they react, and they also want to know how many particles they have.